In this video, we're going to cover section 4.5, graphs of sine and cosine functions, still part of unit 4, trigonometry. Okay, so just to kind of let you know, you do have these in your foldable. We're going to be referring to them frequently. I believe it is under tab number 9, sine, cosine, and a few other ones. We're going to be focusing mostly on these two. Okay, so here's our sine function. Kind of looks like a roller coaster. Okay, and it basically starts at 0, so to speak, and it just repeats in this periodic fashion where you have the same pattern kind of going on over and over. Okay, some important points for this are the key points, which we like to call intercepts, minimum points, and maximum points. Okay, you'll notice that our intercepts are basically every pi. So 0, pi, 2 pi, -pi, -2 pi. I guess one way to note this, so we can also define this, is it's going to be basically n pi, where n is an integer, basically any whole number, 1 pi, 2 pi, 3 pi, 4 pi, etc. And same with the negatives. So n pi, where n belongs to the integers. That's what the little z means here. The second thing you're going to want to take note of are all the minimum and maximum points. So I'm only going to do a few because obviously there's a whole bunch of them, but some of the minimum points here would be, for instance, this one right here, which is -pi halves, -1. This is a min. We have another one over here at 3 pi halves, -1, also a minimum. Okay, and you're going to notice that all of our minimum points are at some kind of pi half and then -1. So -1 is our lowest point all across the board in the entire function of sine. Likewise, the maximum points are on the opposite side. So you're going to have a max up here at pi halves, +1. A maximum here at -3 pi halves, +1. So again, we have positive ones on the top of our graphs, and you'll notice this pattern throughout the entire section of sine. Okay, we're also going to note that sine has origin symmetry, which is the same as odd, which means that if I were to rotate this 180 degrees, it would basically land on top of itself. This point would land here. Our x's and our y's just switch signs. Very interesting. Here's the cosine function. This, and again, this first part of notes is mostly just notes, stuff to copy. This one is really similar in the sense that it has that up and down kind of pattern going on, periodic pattern. But this one, if you start at the origin, starts at 1. So cosine will always start at 0, 1 as far as a good starting point to graph it. And it's going to go down and up. So we have this even symmetry where if you take this line and you fold this piece over, so if I fold this over like that, it's going to land right on top of this side. And just like the other one, we have our intercepts, wrong color. We have intercepts at every pi half plus 1. So in this one, we can think of it like the following. Pi halves plus n pi, where again, n is an integer. So if I take pi halves and I add 2 pi to it or something, I will land on another intercept here on the x-axis, another 0. Okay. My minimums and maximums, I have those as well. I'm not going to label every point. I'm just going to kind of show you. So here we have a min. Here we have a min. Notice that these mins are also going down to -1, and our maximums up here, and up here, these are topping off at +1. So both of these functions are basically oscillating between -1 and 1. And that is important because that does have to tell us, that gives us some information about the range of these functions. The range of these functions is actually going to be between -1 and 1 for both of them. The domain, on the other hand, is basically all real numbers because this pattern goes on forever to the right and to the left. Same with the sine function. All right, let's look at some examples now on how to use these. Lots of examples in this one. we're going to sketch the graph of y equals 2 cosine x on this interval, negative pi halves and 9 pi halves. So we're going to start doing a little bit of some transformations. Okay. If you ever forget what the graphs look like, you can look at your foldable. I'm going to be referring to it frequently just to kind of show you how to use it. For any kind of transformation, whether it's trigonometry or something simple, you always want to start with your original function, the parent function. I like to call it the OG, the original graph of y equals cosine x in this case, because our transformation here, we have a 2 in the front, so we know from past experiences that the 2 in the front is usually going to be some kind of stretch by 2, okay, a vertical stretch by 2. So let's see what that does to this. Here is our cosine function. Remember, it goes from 0, 1, down to pi halves, 0, down to pi negative 1. So we kind of have this little pattern. So we're going to lightly sketch that here. So what we're going to do now is we know that the 2 is a vertical. We used to call it a vertical stretch. There's actually another name for it, but we'll get to that in just a bit. This right here is a vertical stretch by 2, which means all of my y values get multiplied by 2. So put multiply by 2. So they just kind of get pulled up. Okay, so that means that this point right here, instead of being at 1, is going to be at 2. This point, y is 0, so 0 times 2 is still going to be 0. Okay, so what that means that all of my x-intercepts are basically going to be the same, right? So these are all going to stay the same. The ones that are going to change are going to be our maximums and our minimums. So this one's at 2, that means that this one's also going to be at 2. This one's going to be at 2. The negative side, so we have negative 1 right here. If I multiply that by 2, I get negative 2. So that means that all of these points are going to be down at negative 2. Okay, and now I can connect it. It looks something like this. And there we go, the pattern will just continue. So the pink one represents y equals 2 cosine of x. Okay. A couple things about this one. We have a 1 new minimum point. So like I was saying, our minimums get kind of moved down. So I'm just going to pick one. I'm going to pick this one right here. This is pi negative 2. So I can say that pi negative 2 is one of my new minimum points. One new maximum point would be the top part. So let's just use this one, 2 pi positive 2. 2 pi positive 2. Okay, and now we have a definition because we said it was a vertical stretch, but in trigonometry, we actually call this the amplitude. Okay, and we're assuming that's going to be the absolute value of that. So this is always going to be positive. If we do have a negative, it just means the graph flips. So if you have a negative in the front, treat that as a separate transformation. That's a reflection. We're going to look at the number by itself, almost like using absolute value. And what happens is what this looks like is it's half the distance between the maximum and minimum point values. So if we look at the one we just did, okay, between this point, so this maximum and this minimum, that's a total of 1, 2, 3, 4 units. So half of 4 is 2, and that is where this 2 came from. So the amplitude for this one, I guess we can add it now that we know what amplitude is. The amplitude is 2 for this one. And that comes directly from this 2 right here. All right, let's try another one, another example. Example number 2, we have on the same coordinate plane, sketch each of the graphs. So just like the one before, I'm going to sketch my OG first. In this case, it would be sine, okay, because now we're dealing with the sine function. Again, if you don't remember what it looks like, here is our handy dandy foldable, y equals sine of x. There we go, we have 0, 0, pi halves 1, pi 0, and so forth. So I'm just going to sketch those real quick. So there's my OG, and I'm going to go ahead and sketch each of these two things. We'll note that the amplitude for this one, I'm just going to put A, is equal to 1/3, and the amplitude for this one is equal to 3, which means that this one is going to be kind of squished closer. So we can still kind of go with our old transformations as far as this is a vertical compression, but basically my sine function, the y values get multiplied by 1/3. So they get shorter, yeah? I'm going to say 1/3 is about right here. And down here, I'll do it right there, negative 1/3. So this one's going to be like really close, kind of close to the x-axis. So there's that one. The zeros will stay the same because we saw that 0 times 1/3 or times whatever is still going to be 0. So here is my other one, kind of I probably should have made this graph a little bit taller, but that's okay. No big deal. Okay, so it's like a lot more squished. You'll see, and it does keep going, so we can put an arrow. Okay, so this one is this one, 1/3 sine x. You can see it's a lot more compressed. 3 sine x is going to be by 3, which means that my original point is now going to jump up to 3. So let's go ahead and do that real quick. Okay, and there we go. And if you wanted to check, you could even check it with Desmos. Isn't that cool? 1/3, there's 3, and there's the original. You can see our graph here looks really similar to what we have here. All right, next one. All right, our next definition has to do with something that's called the period. The period is based off of this positive real number b. That's what this means. B greater than 0 is positive. B is an element of the real numbers. And it's located here inside the parentheses with x. Okay, it's right next to x. It's given by this, 2 pi divided by b. And basically what it is it's how many times or how much space it takes for one of the, I guess you could say one pattern to happen, one part of the graph to repeat itself. Okay, so far both of the ones that we've done, so sine and cosine, have a period of 2. And if you look at your foldable here, okay, we kind of talk a little bit about that here. It says this interval is called the period, functions period. Basically, it's where it repeats at regular intervals. So we can get it by using the following. And such. I'm not going to read all this to you. You can probably read it, but that's where it comes from. Okay, so our period for sine and cosine are going to be 2 pi. Because if you look back at, I probably should have come back. Let me go back to the foldable. If you look back at this, we have this pattern between 0 and 2 pi is the same as it is over here. So every 2 pi, we have the same pattern. Same thing with cosine. So from 0 to 2 pi, we have this like upside down curve thingy. And if I were to move it over, it's the exact same thing right here. Okay, so the period for both of these is going to be 2 pi. And that makes sense because those functions, their b is equal to 1. So 2 pi divided by 1 is just 2 pi. Okay, and then this part is a little hint because when you are dealing with the b, because it's part of the x in the parentheses, we do have to think of it kind of like division, not so much multiplication. So think opposite. Let's try example number 3. Okay, we're going to sketch y equals sine of x over 2. Step number 1 is to find the new period because we do have a b here. Yeah, this one b is equal to 2. Okay, since we have a b, we're going, actually no, b is equal to 1 over 2. It's 1, there's like a 1 here, right? Imaginary 1. So b is equal to a half. So we're going to have to calculate our new period. So p is equal to 2 pi divided by b. So in this case, 2 pi divided by a half, which is a little interesting because, well, we know when it comes to fractions, there's a little bit more work involved. So let's do that. 2 pi times, flip this one, so I have 2 over 1, which gives us 4 pi. So that means that our pattern is now going to happen within 0 and 4 pi. So what we do second after this is to divide this period into 4 equal parts. Why 4 equal parts? Because those 4 equal parts are what we have in our original graph. We start with an intercept, a max, an intercept, and a min, another intercept. And that's when this whole thing kind of repeats itself. We have 1, 2, 3, 4 pieces in between that. So we're gonna have to do the same thing for this part right here. Okay, these are basically going to be our new key points. So let's go ahead and do that. Okay, so what I'm going to start off with here is I'm going to label my 4 pi. Since I know that 4 pi is the period, this is the number that I have to kind of work with. So there's 4 pi, there's negative 4 pi. And since I have to divide this in, and I'm going to look at it, I'll do this side first and I'll transfer it over to the negative side. So 4 pi is kind of easy to divide into 4 equal parts because, well, it's already in 4, right? So we have 2 pi, okay, 1 pi, and 3 pi. And there are our 4 equal parts. We can do the same thing on this side. So negative 2 pi, negative pi, and negative 3 pi. This is why it's kind of important to find the period first, because this will kind of give you your starting point on how to divide these up. Okay. Then we're going to go ahead and use these values to get our key points. So we know that sine always starts here in the center. And since we went ahead and did this transformation to it, which we'll talk about what the transformation is in just a bit, basically these points become our new key points. So this, remember this is 1, this is negative 1. This first point right here will be our new maximum. Okay, this will be our next intercept. We're just kind of following what we know sine looks like. Okay, 3 pi will be our negative 1, and this will be our intercept. And we have done it. So we have graphed our new transformation. Can you do the OG with this? Yeah, of course. You could graph the original graph first and kind of see. And you know what? We can do that in just a bit. Let me go ahead and finish this one. So on the other side, we have the opposite thing going on. So something like this, like that. Okay, and this represents the one we just did, y equals sine of x over 2. Now, if we go back to our original graph, we know that sine, okay, starts to change at pi half. So just to kind of give you a reference, you can see what actually happened here. We know that sine did something like this, right? But within these two, we already had one period happen. Okay, so maybe something like that. Okay, so I just did a few of the curves of sine. Basically, you can see with my the one that's like kind of dashed, that the new graph is kind of like stretched out this way, right? Isn't that kind of weird? And that does make sense because B, since B is equal to a half and it's in here, this is also known as a horizontal stretch. Remember, B is always opposite of what you think. So even though it's a fraction, it's going to work as a stretch because when we actually work it into x, it gets multiplied and this becomes bigger. Okay, so I'm going to go ahead and make my new graph a little bit darker just so you can see it. The pink one represents the transformed one, and the somewhat dashed one is the original graph. Okay, but again, for this one, you do not have to do the original. I just wanted to do a little bit just so you can kind of see the difference, how this one kind of expanded out that way. Okay, some new key points. Well, now we have a key point here. We have a maximum at pi 1. We have a minimum at 3 pi negative 1. We have an intercept here at 2 pi 0. So just some of the key points to keep in mind. Okay. Oh, and actually, what I just mentioned is right here. Note this is also a horizontal stretch of the graph, which we just showed. All right, let's move on and do the next example. We're almost done, I think. We have some horizontal translations of sine and cosine, and this is what they look like. So lots of stuff to copy. Same rules as before. Basically, if you have a number inside, it's going to be moving to the left or right, okay? A couple things that we do need to kind of mention is if you do have a B and a C, then there's a little bit more work. The best way to think about it is a starting point and an ending point. That way you kind of know between what 2 points to start your graph and where to move it. So we call this a horizontal shift or a phase shift. In trigonometry, they like to give different names to everything. So this is also known as a phase shift. Okay, here's an example, I guess, and let me go ahead and let me just jump into it, and it'll be easier that way. It says describe the transformations and sketch the graph of y equals 2 cosine of x minus pi halves. This one's not too bad because we have no b, so that's going to make our life so much easier. So let's start with our OG. For this one, I am going to do the OG. Okay, so here's our OG. It's the dashed line. I went a little bit over on this side just to kind of complete the curve, but either way is fine. The transformations that we see here, well, first of all, I do see an amplitude of 2. So remember that this part right here, amplitude equals 2, which means that the graph is going to stretch upward and downward. It's going to go up to 2. So that's the first kind of dotted line that I'm going to do. I know that this guy is going to come up here like so. And I'm doing it dash so far because there's still one more transformation to consider. So that one's going to go down there and so forth. Okay. All right, so the pink dashed line represents basically an amplitude of 2. You can think of it like this. This is like y equals 2 cosine x. That's the pink one. Okay. Now, if I go ahead and do that last part, so if I add in this part right here, so now I'm going to do this entire thing. Well, I know that pi halves, if you have a minus, this is actually going to be pi halves to the right. So we have a phase shift, and it's called a phase shift, pi halves to the right. Okay, so we're going to take all of the pink points, because that's the first transformation we did, and we're going to move it over by pi halves, like so. This point would now be here. Okay, this point right here is going to move over pi halves. So there it is. This point's going to move over pi halves. There it is. This point's going to move over pi halves. There it is. And it just follows the same pattern. Okay. This one, oh, sorry, this one's going to move over here. This one's going to move here. This one there. And this one there. So we kind of have something like this. And it's interesting because this actually kind of looks like a sine function now. But, it's cosine. We just moved it. And let's see, we can figure out the rest, something like that. And there you go. So the blue one is going to represent our brand new function. Do you have to do every single graph before? I'm going to say at least do the OG. At least do your OG for this kind when there's no B involved. Because when there's B, yeah, it's a little tricky, but this one's not too bad. Okay, that's it for that one. Let's go ahead and move on. We're going to go ahead and do another example. This one does have a B. So let's see how that looks. We have a vertical translation problem where now we're moving up and down. Okay, so there's a note here that if we do have a D, which is our kind of like our vertical translation, it's a vertical shift or translation up or down that many units. So basically we do the same thing, but now we're going to move our graph up or down. Okay, so right here, right away, I know that just by looking at this, that there's an amplitude of 3. Okay, there is a B in this one. There is a B of 2, and there is a D of 2, which is a vertical translation. Okay, so let's go ahead and I'm going to go ahead and kind of just sketch the OG first, just like I usually do. Or you know what? No, before I do that, I'm going to Notice since we do have a b, we're going to have to recalculate the period. So let's actually do that first. Since we have a b, okay, we're going to have to do a brand new period. Remember, period is 2 pi divided by b, so this would be 2 pi divided by 2, which is equal to pi. So that means that I'm going to have to divide from 0 to pi, I'm going to have to divide that into 4 pieces. Okay, so let's start with that. We're going to go ahead and I'm going to put pi right here. So let's just repeat that on this side. And divide that into 4 pieces. So pi halves, pi fourths, 3 pi fourths. Same thing on this side. So this side should look like this side. That's why I always start with my positive and then just kind of replicate it over here. All right, so there is our new period, okay? And we know that this one is going to do a couple things. It's going to move up by 2 because that's a positive 2. It's going to have a amplitude of 3, so that's why, I don't know if you noticed, but I did quite a few points here. So we have a 3 here, 1, 2, 3, 1, 2, negative 3. Okay, and then it's still going to move up. That's why I had to put a few more points. So there's 5. And yeah, that's about it. So let's go ahead and start plotting this. This is cosine. So if I were to go ahead and do cosine with this in mind, remember that cosine starts at this point right here. This is going to be sort of kind of my OG in this case. So think of it like this. Y, we'll do y prime, equals cosine of 2x. This is what I'm graphing right now, because it's not exactly my OG for my cosine function, but it is going to be my OG with a amplitude, with a period of pi. So this would be here, this would be here. So we have something kind of like this. This is negative 1 and 1. If you need to follow along, see if you can follow along. Something of that sort. Hopefully yours is a little bit better space than mine. All right, so there's our somewhat OG for this with a period of 2. That's why I say when you're dealing with B, you kind of want to work it a little bit differently, just because it does work a little bit different. Okay, we're going to go ahead and apply the transformations now. So I have an amplitude of 3. Okay, so let's do that one first. That means that all of these points are going to jump up to 3. So there's that one. This one's going to stay there. My zeros pretty much stay there. This is going to jump down to negative 3. This is going to jump up to 3. Okay, so we kind of have something like this. Okay, and last but not least, so this would be kind of like y double prime. It would be 3 cosine of 2x. And I'm just kind of going in steps. Okay, the last thing I'm going to do is the one that I actually have. So I'm going to add 2 to it. So now I'm going to do this last one in 2. This means up 2 units. So let's move this entire thing up by 2 units. So there's my new point. This one's going to move up now. So there's my new point at 2. This one's going to move up to negative 1. This one's going to move up to 2. This is up to 5. So I have something kind of like this going on. And yeah, you get the idea. Basically, that's it. Okay, that is it for this topic. Hopefully it wasn't too difficult. It's not that it's difficult, but they do kind of take some time. Okay. And I believe that is the last one. Yeah, but there's one more example. We'll go ahead and do it in class. I will go ahead and stop this one here. Make sure, maybe let's just write the transformations real quick. So this one had a vertical translation up 2. It had a horizontal compression by the 2 in there. I'm just going to leave it as a horizontal compression. And it has an amplitude of 3. Okay? And I will show you the last one just so you can copy it, and we can do this one in class together. So here's the last example. If we have some time, we'll go ahead and go over this one. That's it, guys. Thank you very much.